I'm going to talk about the theory of asymptotic spectra and applications. Here's an outline of what I'm going to do. So there's today and there's next week. I will start with talking about motivations. And there are a couple here. We will focus a lot on matrix multiplication, but I will also talk about Shannon capacity, the capside problem, the sunflower problem, and quantum entanglement. And after these motivations, I want to talk about asymptotic spectra of matrices, tensors, and graphs, and finally, if we get there in time, something about the abstract theory. All right. Let's start. So maybe before I begin with the motivations, this theory is about what happens if I take an object, I raise it to an nth power, I consider interesting property of this object, some real number, take an nth root, and I let n go to infinity. That will be the flavor of many of these, all of these problems that I mentioned here. Okay, so let's start with matrix multiplication. Question?
Yeah, is that side, is the thing inside the limit going to be monotone usually?
This property?
Yeah,
you need to have some property that makes this limit exist. Yeah.
Okay, but it's not going to be monotone. Like the sequence you're taking.
No.
Okay.
No. Yeah. Eventually, maybe it's kind of monotone, but yeah. All right. So I want to start by talking about algebraic circuits. So an algebraic circuit is something of the following form. We have some variables and some constants. And we have some arrows going to other nodes labeled with operators, plus and times, maybe like this. And these a graph like this computes in its in the nodes over here polynomials in a natural way. Let me call them f1 and f2. And so I just naturally evaluate this this graph, and it evaluates polynomials. I want to go the other way around. Suppose we are given polynomials, a bunch of polynomials. What's the smallest algebraic circuit that computes these polynomials at the bottom? Okay. And the problem we're interested in is matrix multiplication. So we're given two large matrices. Let's put variables in them, like this, xij, yij. So they're variable matrices. And we perform matrix multiplication. We get this output, which are polynomials in the x's and the y's. These are the polynomials we want to compute now. And the question is, what's the smallest circuit that computes all these polynomials? Well, so there are n squared polynomials over here, so it's not so hard to see that we need at least our circuit will need to have size at least n squared. And if you do matrix multiplication as you're used to, you will end up with an algebraic circuit with size, let's say, 2 times n cubed. Yeah?
So size the number of gates, we allow one
Yeah.
Out and fan in, or
Let's say fan in 2,
okay.
and let's say we count all the nodes.
Okay.
Yeah. Good question. Okay. So this is the trivial lower bound and trivial upper bound, and we want to know what's the actual algebraic complexity. Now let's make this a little bit simpler. So instead of the actual complexity, we focus on the exponent. So we don't care about the c in front of the n. We just want to know what's the optimal omega in this complexity. And what's currently known is that this omega is between 2 and 2.37, roughly. Okay, so the upper bounds come from algorithms, and the lower bounds come from some kind of obstructions or lower bounds, right? The non-existence of algorithms. So there's been a lot of, so this is what we know now, but it took a while before we got here. So the first result on this was in the 60s by Volker-Strassen. Let me draw a graph. So the trivial upper bound is 3, so that's where it all started. And 2.0 is the trivial lower bound. And Strassen in the 60s managed to bring down this exponent to 2.8. And then it took a while, so this was in the 60s, and then it took a while, somewhere in the 80s, for people to come up with new tools to bring this down to roughly 2.5. So this brought down. And a little bit later, this was brought down to a little bit above 2.3. So, okay. So this is, there has been some very recent work improving these bounds a tiny bit. This is like in 2018, or a little bit earlier, 2000s. So this is the curve of the best upper bound that people have proven. The lower bound did not move. So the lower bound of 2 stayed at 2. Okay, so this is the best upper bound on omega. This is the best known lower bound. On omega. Okay, so that's the state of the art. Yeah, I should mention that many interesting tools were developed along this in this history. In particular, around this time, Strassen, in 3 papers, developed the theory of asymptotic spectra for tensors. Okay, so that's where this theory comes from. So here we have these papers of Strassen, which you can think of as a theory of lower bounds. And what we will see next week is that we can use this theory to prove barriers for certain methods of constructing algorithms. So we won't improve the lower bound, but we will prove that if we restrict to a certain collection of methods to construct algorithms, then we can prove barriers. So we can prove that we cannot go below, say, 2.3 in certain cases. It depends on which methods you consider. Okay, so.
Do we expect the lower bound to
Say it again?
Do we expect the lower bound to
It's possible. I don't know. Yeah. Some people don't expect that, yeah. Yeah, I don't know. All right. So let's move on. So this is the problem. What's omega? Let's phrase this as an asymptotic tensor problem. I'm going to talk about tensors more later. So this is more of a connecting part. So what we need is something called the matrix multiplication tensor. So first of all, tensors are three-dimensional arrays. I'm going to say more about this later. But for here, let's say there is a matrix multiplication tensor. Let me write it down. It's a sum over ijk from 1 to n of this outer product. So eij, tensor ejk, tensor eki. So this tensor lives in has dimensions n squared by n squared by n squared. And the point of this tensor is that if you consider its tensor rank, which we will also be talking about more later, then this tensor rank denoted by R is roughly the same as the algebraic circuit complexity of matrix multiplication. Okay, so that's why I'm going to talk about tensors later. There is one more interesting property about these tensors, and that's a recursivity property. So if you know this from multiplying matrices, if you have block matrices that you want to multiply, then you can multiply them blockwise. And for the tensor, this means that if you take a matrix multiplication tensor, then if you tensor it with another one, maybe of a different size, then you get a bigger matrix multiplication tensor. All right. I'm going to speak more about this product later, so don't worry about that. The punchline here is that this exponent omega that we are interested in, the exponent of matrix multiplication, it arises as a limit of n going to infinity of the rank of the nth power of the matrix multiplication tensor, the smallest one, 2 to 2, to the power 1 over n. Okay, so we have this problem we're interested in. I now phrased it as this asymptotic problem. Good. So we will talk about tensors more later. Sorry?
It is the same omega?
This is the same omega, yeah. This is the matrix multiplication exponent. Yeah. Okay, cool. So that's the first problem. So let's go to the Shannon capacity. All right. This is a problem about communication. Yeah.
Okay, so just the word from the notation over there. So you're taking two n squared by n squared by n squared three-dimensional tensors and tensor will be another three-dimensional tensor?
That's correct. Yeah. This is a three-dimensional tensor, order 3 tensor. This is also order 3 tensor. You tensor them together, and it again becomes an order 3 tensor. I'll give the definition later.
Also EIJ, like EIJ are, what are they? Like, what are they different numbers?
These are basis elements.
Okay. Oh,
This is an outer product.
back towards the okay.
Yeah.
So it's a vector of n squared coordinates with 1 in the ij.
That's right. Yeah. And then you take the outer product. So it becomes a three-dimensional array with one element. One non-zero element.
Which is a 1.
Which is a 1. Yeah. Okay. Let's talk about Shannon capacity for a bit. This is motivated by a problem in, comes from a problem in communication. So let me start there. We're given a communication channel. For example, this channel. It has inputs 1 to 5 and outputs A, B, C, D, E. Let's make it a little bit more interesting. So there are some arcs going across like this. So what does this channel do? You input a 1, and it gives you either A or B on the other side. Same for all the other, similarly for all the other inputs. The goal is to communicate without any error. So if the receiver receives an A now, the receiver doesn't know whether it comes from a 1 or a 5. So that's not good. So what we do is restrict the inputs to a subset so that there will be no collisions in the output. So for example, we can restrict to the inputs 1 and 3. Then if the receiver receives a B, say, then the receiver knows it came from a 1. So we have 0 error communication. So if we use this channel once, we can send 2 symbols. Say 1 and 3. The goal is to use this channel more often. So instead of sending a single symbol, we will send pairs of symbols. So we get a new diagram then, where the inputs are pairs. So for example, 1, 1 is an input, and 1, 1 will be sent to AA, AB, BA, or BB. Yeah, and similarly for all the other pairs, we know where they go to, just following how this channel would do it. But now there's this special interesting thing that we can actually use this channel more efficiently, this channel. Namely, we can pick this set of inputs, 1, 1, 2, 3, 3, 5, 4, 2, and 5, 4. So that's 5 pairs. And you can check that if you pick any 2 of these pairs, then they will be distinguishable. For example, we pick the first 2 pairs. We see that the first 2 symbols, so 1 and 2, they might get sent to the same letter. But 1 and 3 will not be sent to the same letter. So we can distinguish these 2 inputs. Okay, so this is the motivation. Let's turn this into a graph theory problem. So the first step is to forget about the outputs. We construct a confusability graph. So I have a graph labeled with vertices labeled by the inputs. So 1, 2, 3, 4, 5. And I connect them whenever they can be confused in the output. And then the goal is to find a subset of the vertices that's independent. So this is C5. That's the goal if you use the channel once. If you use the channel twice, then you get a new confusability graph, which I'll for now denote by C5 squared. Okay. So as I mentioned, we're interested in the independence number, alpha G, which is the size of the largest independent set in the graph. And then we consider this asymptotic property called the Shannon capacity, which is a limit of n going to infinity of alpha of g to the power n to the power 1 over n. So this is called the Shannon capacity. All right. Let me give an example of that somehow shows the state of the art. So for this 5 cycle, we know what the Shannon capacity is. that is in fact square root of 5. That's a result of Lovaas. But for example, if we go to the 7 cycle, so I take the same graph with 7 elements, we don't know what the Shannon capacity is. So Polak and Schrijver proved that it's at least 3.25, and Lovaas proved it's at most 3.31. Okay, so that's the state of the art. So for small graphs, we don't know how to compute this Shannon capacity.
The 3.31 also from the Taylor function?
That's correct, yeah. Okay, good. Yeah?
Which bound do most people believe is correct?
I'm not sure. I didn't do a poll. Yeah.
I mean, like, there's no.
You mean of?
What about just the computation where you go up to 100?
I think people don't believe that this is correct. Yeah.
Okay. Is it just from like going up finite case check or something?
This comes from they consider the 5th power, and they construct an independent set in C7.
Okay.
That's how it goes.
Okay. I see.
Yeah. Good. All right. Okay, let's talk about the capset problem. So, in the capset problem, I want to make the following definition before stating it. Let's take 3 elements x, y, z in z3z to the power n. We say that these elements form a line. If we can write the triple xyz as a triple u, comma u plus v, comma u plus 2v for some u and v in z3z to the power n. Yeah, so it's just saying that x, y, z lie on a line. And let's say that v has to be non-zero. The question here is, how large can a line-free subset S of z3z to the n be? And there was recently a breakthrough on this problem. So before we didn't have any non-trivial upper bounds on this problem, but then Ellenberg and Gijswijk proved that such a set has size at most 2.755 to the n. It's Ellenberg, Gijswijk. And before it was known that it has to be at least 2.4 to the power n. It's by Adel. So this is a construction, the lower bound, and the upper bound is by some clever mathematical tools, which we will see. Good. Excellent. So let's say something about the sunflower problem. I'll go here. we're given here 3 sets, ABC, subsets of the numbers 1 to n. And we say that they form a sunflower. If the pairwise intersections are all the same. So they are like this. And then the question is, how large can a sunflower free subset S be?
The average number of sunflower,
That's right.
not the origin layer Toronto.
That's right. Yeah. But Erdős liked it, so that's okay. How large can a sunflower free subset S of the power set of n be? With similar tools as the tools that were used to solve the capsule problem, we now have this upper bound on the size of S, which is 1.88 to the power n. This is by Naslund, Savin, and there is a lower bound of 1.55 to the n, also by Naslund. Right. Okay, so then we get any questions about this? Let me get to the last motivating example. And that's quantum entanglement. So I don't expect anyone to know anything about this. But let me say something on a high level. In this problem, there are 3 players, 3 systems, Alice, Bob, and Charlie. They correspond to these dots. And they are sharing what's called a quantum state. And a quantum state, mathematically, is simply an element in C n cross n cross n. So it's a 3 tensor. Now, different states have different applications. Good, thanks. Different states have different applications. So, for example, some states are useful for teleportation, others for cryptography. So we're asking suppose there are 2 states, phi and psi. Can we transform one state into the other without using any additional resources? So by just doing local operations on your system. And maybe some classical communication, but never mind. Let's make it a little bit easier. So we're given not 1 copy of the state. Let's say the 3 parties together, they are given n copies of the state. So phi to the power n, a huge bunch of copies of phi. And their goal is to, by some local means, transform this into many copies, so alpha times n copies of some other state of psi. The question is, what's the largest rate alpha that you can achieve? So that's the quantum entanglement question. Okay, good. So these are the motivations. These are the motivating questions. And then I want to start talking about the asymptotic spectrum of matrices, if there are no questions.
Say what the balance sounds.
Good point. That will depend on phi and psi, which so maybe I won't go into it. There are many results if you specify for me which phi and psi to take. Yeah. We'll see a couple of examples later. Okay, good. So this is all examples.
About the quantum entanglement thing, the way you're given, you're ultimately, when you eventually discuss it, describing the states phi or psi, are they given as density matrices?
Let's say pure quantum states, but you could consider other variations. Yeah, but let's say they are pure quantum states, and you could consider what's called SLOCC, Escher operations, so stochastic local operations and classical communication. But you can consider many other variations.
But if you only had Alice and Bob, it would be.
That would make it a lot easier. Yeah, there's a big, and we're going to see this actually when we talk about matrices and tensors. Matrices are going to be a lot easier, and that's exactly the same question. Yeah. Right. So, let's start with the asymptotic spectrum of matrices. So let's consider two matrices, M and N. I want to define on these matrices a relation. We'll say on any two matrices, M is smaller than N, if there exists two other matrices, A and B, of appropriate sizes such that M equals A times N times B transpose. Transpose is not very important. And I could also denote this by A comma B times N. Okay? So M is smaller than N if I can obtain M from N by left and right multiplication. This definition is nice because it gives us, in a very natural way, the matrix rank. Namely, the usual matrix rank of a matrix M equals the minimum number N such that M is smaller than the N by N identity matrix. There's an interesting thing, a second characterization of this matrix rank as a maximization. I can write it as a maximization over N and N, such that the N by N identity matrix is smaller than M. And the reason that these are equal is Gaussian elimination. So if you want to prove this fact, you use Gaussian elimination. So this is my pre-order, and it's motivated by this rank. Now, I think we all know the Kronecker product of matrices, right, where you multiply each element in M with n as a block. You do this throughout the whole matrix, etc. So this is the Kronecker product of matrices. And we all know the direct sum of matrices, which we just get by putting our matrices like this, putting zeros here. Now here comes the theorem, and this is the end of this section. This is the main theorem, and it's very simple. We consider a set X of matrices. This is the asymptotic spectrum of matrices, which is defined as the set of all maps phi from the set of matrices to the real numbers, non-negative real numbers, such that four properties hold. We want phi to be multiplicative under the Kronecker product. So phi of m times n is phi of m times phi of n for any m and n. I want phi to be additive, so phi of m plus n equals phi of m plus phi of n. Phi has to be normalized in the sense that phi of the n by n identity matrix equals n. And I want phi to be monotone under my relation that I defined here. So if m is smaller than n, then I want phi of m to be smaller than phi of n. So that's the definition of this set. Then the statement of the theorem is that this set X of matrices equals just the set containing the matrix rank. So the matrix rank is the unique function that satisfies all these properties. So this is a very simple situation. I wanted to start with this because we all know what's going on here. Yeah.
Why does a preorder basically not already correspond to rank? Like, isn't matrix M the most? This is the following is not true, right? Matrix M is at most matrix N if and only if rank of M is at most rank of N. This is not true, right?
It is true.
Oh,
yeah.
that is true.
Yeah.
Okay.
Yeah.
Okay, so this preorder is basically just rank in a disguised form.
Yeah. Right.
Okay.
Mm-hmm. Yeah. Correct. Right. So let's go to tensors, where it will get a bit more interesting.
Yeah.
Right.
I thought so.
Yeah. Good point.
All of these actions necessary, like if you remove any one of them, is the conclusion stops being
I
true?
think you can get rid of some of them. Yeah, I think maybe the second you don't need, for example. Yeah. Normalization you do need, but yeah, it's not so important maybe. Yeah. So now that we have the situation for matrices, I want to go to tensors, and now we can work by analogy a little bit. So that's nice. So what are tensors? They are three-dimensional arrays. So let's take two of them, T and S. And they're indexed by triples because they're three-dimensional arrays. Let's say over the complex numbers or some other field. And again, I want to define a relation on my tensors. I want to say T is smaller than S if now there are three matrices ABC of appropriate sizes such that T can be obtained from S by multiplying S on all sides with A or B or C. So I can write that as A, comma B, comma C dot S. Somehow generalizing the notation I was setting up over there. I can also write it out as follows. So it's a sum over little a, little b, and little c. A, I, A, B, G, B, J, B, C, K, C, S, A, B, C. So this will be the ijkth entry. All right. Now let's follow the thing we were doing before. So before we started talking about matrix rank. So let's do this. There's the notion of tensor rank, and indeed it turns out that the tensor rank of T, which people talk a lot about in tensor theory, equals the minimum number n such that T is smaller than the n by n by n identity tensor, which is just an n by n tensor with ones on the main diagonal and zeros elsewhere. Because this is the tensor rank. What happens if we take the other definition and apply it to tensors? It turns out you get something entirely different. So this is called the subrank of a tensor. It's denoted by Q of T. And it's this maximum over n and n, such that the n by n identity tensor is smaller than T. Now I want to define a product and a sum, as we did before. The Kronecker product for tensors, T tensor S, is defined as follows. So you have two order 3 tensors. You tensor them together and it again becomes an order 3 tensor, but now it's labeled by triples of pairs. So if I look at the coordinate IA, JB, KC, I just see the product of the ijkth entry of T and the ABCth entry of S. That's the definition. The direct sum is easy to define in a picture, so you just take your tensor T and you put your tensor S next to it such that they touch in one corner, and the rest is 0.
Can you give some example of how Q is different from R?
So a very silly example is when you take a tensor of the form E1, tensor EI, tensor EI, and you sum over I from 1 to n or something. then it's not hard to see that the tensor rank will be n, but the subrank will only be 1. So this tensor really lives in f1, n, n. If I want to obtain a large in from it, the largest I could possibly get is as dimension 1. This is the example.
There's more freedom in 3 dimensions, sort of, so you can have something that is gap. There's like more things, right? Because it's like more freedom in 3 dimensions, right?
You could also say there's less freedom. In some sense, the group that you're using is...
Yeah. Sorry, I mean, there's more freedom for the tensors to avoid what you're trying to get. There's less freedom with what you're allowed to. Right, okay.
It's not super because you're conjugating with something two-dimensional, kind of.
Yeah.
There are much fewer parameters in A, B, C than in S.
Right.
Well, before you were conjugating with the same sized object.
Exactly. Yeah, I think that's a very good intuition. So, all right, so we've covered that. Now, before the tensor rank, the matrix rank is well known to be multiplicative and additive, and we also saw that in the theorem. It turns out that tensor rank is not multiplicative under this product, and also subrank will not be multiplicative under this product. Therefore, it's interesting to look at the asymptotic versions of tensor rank and subrank, called asymptotic rank, r tilde t, which is, as you might guess, this limit of n going to infinity of the rank of t to the power n to the power 1 over n. This limit exists, which follows from the fact that rank is submultiplicative. And then you can use something called Fackett's lemma to prove that this limit exists and actually equals the infimum of the same expression. So instead of the limit, you could put the infimum over n. And we do the same with the subrank. It becomes asymptotic subrank. It's the same thing, but then with the subrank. Subrank is super multiplicative, so instead of limit, I could put supremum. Okay, so to give an overview of the parameters we have now, we have the subrank. We have the rank. It's not hard to see that the rank should be bigger than the subrank, right? Because the rank is how large of an in do we need to create t, and the subrank is how large an in can we create from t.
But it's still a gap between them, right?
But there is a gap, yeah. And these parameters are actually in between. So the asymptotic subrank is lower bounded by subrank, and the asymptotic rank is upper bounded by rank, and they also satisfy the middle inequality. So that's the situation. And these inequalities can all be strict. I'll give you the example, and we'll see the tools later to prove this. The example is the following tensor E1, tensor E1, tensor E2, plus the 3 permutation, the 3 cyclic shifts of this. So E1, tensor E2, tensor E1, and E2, tensor E1, tensor E1. This is sometimes called the W tensor by people in quantum information theory. And here, if you manage to compute these numbers, what you end up with is a subrank of 1, an asymptotic subrank of 2 to the power the entropy of 1/3, asymptotic rank of 2, and a rank of 3. So we see that some of these parameters are sometimes not integers, so that's interesting. We see that they can all be different. Right.
Can they all be distinct integers, or
Hmm?
can they all be distinct integers, or?
I'm not sure. I don't know. I don't know. So let's now define the asymptotic spectrum of tensors by analogy. So let's say X, or X of tensors, is the set of all maps phi from all tensors of all possible sizes to the non-negative real numbers, such that we have the following four properties again. I want phi to be multiplicative. I want phi to be additive. I want phi to be normalized on these n by n by n identity tensors. And I want phi to be monotone, meaning for any t in S, if t is smaller than S, as we defined before, then I want phi of t to be smaller than phi of S. That defines X. So what happens now? With this set X. What can we do with it? Well, there is a simple observation. Let me call it a lemma. That for every phi in X, we don't know what they are, but let's take any phi in X. We have that the asymptotic subrank of t is upper bounded by phi of t, and the asymptotic rank is lower bounded by phi of t. Okay. So this follows directly from the four properties. You don't need all four, you need only three of them. So I will give this as an exercise. This is not hard. So that's a nice tool. So if we want to lower bound asymptotic rank of a tensor, then we just need to find these phi's and we evaluate them, and that's good. And if we want to maybe upper bound asymptotic subrank, then we find these phi's and we upper bound asymptotic subrank. But how good is this tool? Well, that's the theorem of Strassen. It says that you obtain the asymptotic subrank by minimizing phi of t over all phi in X. And similarly, if we maximize over phi in X, we will obtain the asymptotic rank. Yes?
But only the sub-rank is a valid choice for phi or something?
Neither of these.
Neither of them is a valid choice.
Yeah. Let me write that down. So it could have been the case that asymptotic subrank or asymptotic rank were elements of X. And then these two statements would be trivial. But they are not. So let me write it as a remark. The asymptotic subrank and the asymptotic rank are not elements of X.
Really a min, not an inf.
Yeah, it's a min. Yeah. So for any t, you will find a phi. Yeah. That's right.
So what prevents them from being in X, these guys?
They're not multiplicative. Well, yeah, they're not. The
Yeah.
T is actually multiplicative.
So the simplest example I have, right. The simplest example is related to matrix multiplication. So what you do is you take, well, we consider the 2 by 2 by 2 matrix multiplication tensor. And we observe that you can write this tensor as a product of 3 smaller tensors, namely the 1 by 1 by 2 matrix multiplication tensor, the 1 by 2 by 1, and the 2 by 1 by 1 matrix multiplication tensors. Then if you roll out the definition, you'll see that this guy, or any of the other 3, but they're just permuted versions, are actually this guy for n equals 2. And for these, it will be easy to compute the asymptotic rank. And then the asymptotic rank of this tensor will be much smaller. So here the asymptotic rank will be, let's see, I should say it right. It will be 2. This guy will be 2, this guy will be 2, but this will be definitely smaller than 8. Because 2 to the omega will be smaller than 2 to the power 3. That's the reason. All right, so that's X, but what's in X? That's a good question.
Prove X is not empty.
Yeah, exactly. Yeah, let's first prove X is not empty. Yeah. Let's this one.
So the word spectra refers to elements of X?
The asymptotic spectrum is the set X. Yeah. Yeah, it's a bit of a funny terminology.
Where does it come from?
I think it comes from semi-algebraic geometry, like when you take the spectrum of a ring. I think that's the origin, but it's pretty old, actually, the origin of this. Yeah.
In the matrix case, is there a simple example of a submultiplicative map that's not right?
Not sure. I don't know. I don't have it. Yeah, it's a good question.
Norms?
Yeah, maybe.
Matrix norms?
Yeah, maybe matrix norms, but maybe you also want it to be monotone. Or
The tensor? Oh, yeah. Yeah, that's a good example.
so is X empty or is it not empty? Well, yeah, we know it's not empty because of this theorem. So we do know that, but we can also give some explicit elements in X. So that's going to be this example. In this example, I construct 3 elements in X. And they come from the 3 flattenings of your tensor. So you have a tensor T, a 3 tensor. We consider the 3 possible flattenings of T. Let's call them T1, T2, and T3. You get them by grouping together 2 of the indices. So I take T, but now I group together the J and the K as if it's one index. Then it becomes a matrix. And these guys arise by grouping in the 2 other ways. Okay, so I can turn my tensor into a matrix, and for matrices we understand very well how to make multiplicative maps or elements in the spectrum. So let's just try that. So we define Ri as the map that sends the tensor to the matrix rank, of the ith flattening of the tensor. And this indeed turns out, that's not hard to check, that it's in X. So these are the first 3 examples, very simple examples. And the big open problem here is there a tensor T with the maximum of these flattening ranks strictly smaller than the asymptotic rank of T. Okay, so we don't know that. And so there are lower bounds. We can take the maximum over them, it's a lower bound. We don't have any gaps there. So this is, this is the first example of 3 elements. It turns out that there is an infinite family of elements in X, and that's what we're going to see next week. And next week we'll also see how to use those elements to prove barriers for fast matrix multiplication. So next week we'll see these infinite families. In X and barriers. So I propose to do a break and then we're going to talk about graphs. We've seen the asymptotic spectrum of matrices, which is just the matrix rank. And so that was not too interesting. But then we looked at the asymptotic spectrum of tensors, and we saw that there are at least 3 elements in here, these flattening ranks.
Probably even 5.
And maybe even 5 and more, yeah. So there will be, no, those are not in there, Q tilde R tilde.
How many elements are actually is it countable?
But there will, no, it's not countable.
Oh, okay. There aren't counted many elements.
Can you take like linear combination of the coordinates and
In some sense, there will be some convexity. There is some convexity structure going on, but you cannot just take a linear combination or a geometric average. That doesn't work. You have to do something more clever. What we're gonna do now? So I now want to talk about the analogous situation for a completely different set of objects, namely graphs. It's not completely different because graphs, you can also think of them as matrices, but the operations and the pre-order, like the relation on them, will be different. And let me mention that there is this general theory which in some sense applies to both. And we will see this a little bit in the end, hopefully. So let me just remind you that here we saw that if we minimize over f and x, we get the asymptotic subrank. And if we maximize we'll get the asymptotic rank. This guy is important for matrix multiplication. This guy will later turn out also to be important for matrix multiplication, and it will be important for problems like the capset problem, maybe also the sunflower problem, etc. Here, the analogous parameters will be the Shannon capacity of a graph. So this will arise as a minimum. Oops. And something called the asymptotic clique cover number. That's chi bar tilde, which is the maximum. What am I doing? Sorry?
What was the name
This is the asymptotic Clique cover number. Yeah. Chi bar is the Clique cover number because it's like the chromatic number of the complement of the graph. So, but this is just to link things a little bit, because now we're going to go into the definitions. So, the asymptotic spectrum of graphs. So, we're going to talk about graphs. So, a graph has a set of vertices and a set of pairs of vertices called the edges. And let's say there are no self-loops. Examples are the cycle graph. Cn, which has vertices, has the numbers 1 to n. And as edges has consecutive pairs. So 1, 2, 2, 3, 2, 3, up to n1 to make it this cycle. We saw C5 and C7 in the beginning. Let me also define Kn. That's the complete graph. So it has, as a vertex set, all vertices, all elements 1 to n. And as edges, it has all pairs. Yeah, so for example, we have K4, and we have C5. And we'll be using the complement of a graph, so let me define that. So for example, K4 bar, you get by taking the complement of the edge set, so in this case it would just be 4 vertices. And C5 bar, we take the complement of the edge set, but if you look at the graph, it turns out to be again C5. So this is isomorphic to C5. These are the basic definitions. Define a relation on graphs, like before, we did for matrices and tensors. So I take two graphs, G and H, and I say G is smaller than H if there is a map F from the vertex set of G to the vertex set of H such that for any two elements U and V in the vertex set of G, if they're different and they're not an edge, then I want that their image is different and not an edge. Another way to say this, which is maybe more natural, is G is smaller than H if, equivalently, if there is a graph homomorphism from G bar to H bar. Graph homomorphism maps edges to edges, and if I put the bars, then what happens is I'm mapping non-edges to non-edges. I want to be precise about the fact that what non-edges mean. So non-edges are two different elements that are not an edge. Okay. So here's an example. I take this graph that just has two vertices, so that's K2 bar. And I take the 5 cycle. Then we have this inequality. So what do we need to check? We need to take any two different vertices that are not an edge. So we take these two. And we need to see that we can map them into two non-adjacent vertices on the right. So that we can just do. We map it to any independent set, so for example here. But if you would now take 3 elements on the left, then it's not possible to do this. So as you see already, I'm moving towards the independence number. Let's first make these two definitions again. We define the subrank of a graph as the maximum number n, such that kn bar is smaller than g. So kn bar is just n vertices, no edges. And we define the rank of g as the minimum number n, such that g is smaller than kn bar. Then here comes a lemma. Saying that this subrank q of g equals the independence number of g. Okay, so that's why this definition makes sense. And you can also look at the rank and observe that this equals the Klikover number of g, which maybe we don't really talk about now. Let me not give the proof. It's a simple proof. It follows from the definitions. Yeah. As before, I want to define a product. And it's called the strong graph product. And it's defined as follows. So if I take two graphs, G and H, then the vertex set of their product is the Cartesian product of the vertex sets. So the vertices are pairs. And the edges are pairs of pairs. Such that, so GH, G prime, H prime, such that G equals G prime, or GG prime is an edge, and H equals H prime, or HH prime is an edge. That's a definition. That's what's actually easier is to take your graph, take the adjacency matrix of the graph, so of G and of H, and then take the Kronecker product of those adjacency matrices. That's the same definition. Okay.
What about the identity?
Good point. So you take a graph, take the adjacency matrix, make sure there's all ones on the diagonal, then take the Kronecker product. Yeah. That's right. So this will be our multiplication. Our addition will be given by this joint union of two graphs, which is really what you think it is. So you take a disjoint union of the vertex sets and of the edge sets. All right.
What about the case that G is equal to G prime and H is equal to H prime? Are we not allowing that?
In the disjoint union?
It would be a self-loop, right? So
You talk about the disjoint union? Or?
in the definition of the edge set, we're not going to put a self-loop around the vertex, right? So
Yeah, we don't put self-loops.
so we don't allow the case that
That one we ignore. Good point. Thanks. Yeah. It's the Klikover number. It's equal to the chromatic number of G bar. So it's the coloring number of G bar.
You want to call the vertices.
Yeah. Yeah. All right. Now, before we looked at the asymptotic subrank, so let's do that again. The asymptotic subrank of G is this limit of the subrank of the nth power of G to the power 1 over n. The subrank is the independence number, so this will be the Shannon capacity. Okay, so we've made that connection now. And then we consider the asymptotic spectrum of graphs. Again, which is this set of maps phi from graphs to reals that satisfy these four properties again. So we want the multiplicativity property again under the strong graph product. We want we want additivity under the disjoint union. We want phi to be normalized, meaning in this case that phi of kn bar equals n. And we want phi to be monotone. So if G is smaller than H, then phi of G is at most phi of H. So that's the definition.
different ordering or a different kind of graph product, you would get something interesting, or only this is interesting?
Well, many things are interesting. If you pick other products or sums or pre-orders, then sometimes usually I don't know how to prove what's coming now. Yeah, I think there are many interesting variations. Yeah, definitely. This is one I can prove something about.
Just one related fact that like Shannon capacity is multiplicative under like 6 different products, I guess.
Or you mean the independence number? What did you say? Sorry, can you repeat?
Shannon, sorry. The theta function is
Oh, yeah, good point.
under like
Yeah.
6 different products.
The Lova's theta function is, yeah, that's correct. Yeah, it's multiplicative under all kinds of other products. Yeah, yeah, right. So here's the theorem about this. We can reach the Shannon capacity by minimizing over all elements in X, F evaluated at G. For every G, we can obtain the Shannon capacity like this. Again, this is only interesting if the Shannon capacity itself is not actually in X. And that's true. The Shannon capacity is not an element of X. And there are 2 examples for this, yes?
So what's the pointwise maximum of
So-
Vg? What's the pointwise maximum? If Shannon capacity is the pointwise minimum, what's the pointwise maximum?
Yeah, that would be the asymptotic Klikover number. Yeah, I wrote it here. I will not write it again. Yeah,
Sorry.
yeah,
Okay.
yeah. Yeah, I'm focusing on the Shannon capacity. But Yeah, okay, it's actually a good point. So the Shannon capacity is not in there. The other guy is actually also in there, but let's leave it. Let me write it and then. Yeah.
So graphs are in between tensors and matrices.
Yeah, it's kind of a weird combination. Yeah, exactly.
Graph 2.5.
Right. So there are two examples for there are two reasons we know that the Shannon capacity is not an X. The first is by Hamers. He showed that Shannon capacity is not multiplicative. So he found G and H such that the Shannon capacity of G times H is strictly bigger than the Shannon capacity of G times the Shannon capacity of H. And Alon proved the same thing for addition. So that's how we know it. So we will come back to this example later, actually. Let me say something about X. So what do we know about the elements in X? We have some knowledge. Let me write that down. So what do we know about X? The first thing I want to mention is the Lovász theta function. I'm not going to define all of these because that will take too much time. But the Lovász theta function is a semi-definite program. And it has been used to compute the Shannon capacity of C5, for example. And it's efficiently computable, which is nice. So that's an element. That turns out to be an element in X. Other examples here are the asymptotic Clique-over number, as I mentioned, which turns out to be equal to the fractional Clique-over number. There is a variation called the fractional orthogonal rank, which is like a linear algebraic version of this one. And we have an infinite family over here called the fractional Hamers bounds, or fractional min ranks. These are parameterized by fields. So for every field you get a parameter, and it turns out that for every characteristic you actually get different ones. So there is a result that says that they are incomparable. So through this we see that there are infinitely many elements in this set X. I don't want to say much more about it now, so you can ask me offline if you want. So next week I will talk more about tensors, not so much about graphs. Yeah, there is another result I should mention that tells us how you can interpolate between points in the spectrum. Like 2 points, there is a way of getting an infinite family between them, some kind of convexity result by Peter Vrana.
Uncountable family, or?
Sorry?
Is it an uncountable family, or?
Yeah, that gives you an uncountable.
Okay.
Between any two.
Yeah,
This real number.
Yeah.
Like between 0 and 1, parameterizing number.
Yeah.
Could you maybe briefly mention like what this theory of asymptotic spectra implies about Shannon capacity? What was not known that is now known?
Yeah, I will mention something at the end.
Okay.
Yeah, I think I will do the abstract thing first a little bit, and then I'm going to say something about it. Yeah, good point. We can also do the other way around. Let's do the other way around. Let's do those first.
Sorry, I didn't mean to.
No, that's okay. So the first. Yeah, exactly. The first thing that follows from this duality. I think of it as a duality. I didn't say that word before, but the Shannon capacity is naturally a supremum. It's this limit, which we can also write as a supremum, so it's like a maximization. And here we write it as a minimization, so it's like a dual characterization of that parameter.
Like are they related though, being the maximum of alpha gn to the 1 over n and being the minimum of phi g? Like why are these dual? Like how are they related?
Well, they're dual because you get the same. I'm just saying you have a parameter which is naturally a maximization, and now we very naturally write it as a minimization.
They're completely different things. So I don't know.
I think the main problem is that we don't know what x is. If that's that might be your. I agree with that. We don't know what x is, so in that sense, it's not a very effective duality. But
like duality usually is the same kind of context, and these are like completely different.
is it true? I mean, I don't know. We can talk about it, but it doesn't. So what's interesting is, and it's true, we don't know what x is, but still we get some interesting consequences from the duality. And this one is one of them, saying that the Shannon capacity is multiplicative if and only if it's additive. So what do I mean by that? I mean that if I take any graphs G and H, then the Shannon capacity is multiplicative. Let me just write G times H equals theta of G times theta of H, if and only if it's additive. So Shannon capacity of G plus H equals Shannon capacity of G plus Shannon capacity of H. Yeah. Yeah, let me just write it down.
Spectra is very hard to write.
Yeah, I know. And then you end up writing a circle with an H in it. Yeah. Yeah. So the proof.
And a theorem or
This is a theorem, or a consequence. Let's say, let's call it a consequence. It was Ron Holtzman who actually mentioned this to me. I hadn't observed this before.
consequence of what?
Of this theorem, of this duality, this theorem.
So this just if for every graph it is multiplicative, then for every
No, you pick any two graphs, fix them, and then if you know this, then you don't know this, and the other way
so
around.
otherwise it's not very interesting.
False statements are equivalent.
Right. So let's do the proof. Let's do one direction of the proof because it's actually a nice proof. So let's say we suppose that we have multiplicativity. Yeah, so we start with the top statement. Then we know that there exists an element phi such that theta of G times H equals phi of G times H. Right? Because we can write Shannon capacity as a minimization. Now we assume this Shannon capacity is multiplicative, so we have Shannon capacity of G times Shannon capacity of H equals Shannon capacity of G times H equals phi of G times H, and phi is multiplicative, so this equals phi of G times phi of H. Now let's look at this. We know also by the theorem, if you like, as a reminder, that the Shannon capacity is at most phi of G, and the Shannon capacity of H is at most phi of H. But we also have this equation, so we now know that the Shannon capacity of G equals phi of G, and the Shannon capacity of H equals phi of H. And then we move to adding the graphs. Shannon capacity of G plus Shannon capacity of H is at most Shannon capacity of G plus H, which is at most 5 G plus H, which is equal to, let's do phi G plus phi H equals Shannon capacity of G plus Shannon capacity of H. So that's the proof. And this, in the other direction goes the same, right? So that's a nice corollary, and it connects these two facts that I stated earlier, that the Shannon capacity is not multiplicative and not additive. Right, so maybe I give this as an example of this corollary. So it says that these results of Hamers and Dallon are equivalent in the sense that if you know that G and H that make it not multiplicative, then you know that they also make it not additive. And another example I'd like to mention is that the Shannon capacity is not attained at a finite power. In general. This is well known. I'm just giving it as a nice example. And the way to quickly do this is that you take C5 and you multiply it with K1, just one vertex, and we consider the Shannon capacity of this product. Now C5 times a vertex is just C5. So this just equals the Shannon capacity of C5. And the Shannon capacity of one vertex is just 1, so that I can also write if I want. So here we have multiplicativity of Shannon capacity for these two graphs. So we also have additivity. So we get the Shannon capacity of C5 disjoint union of vertex is the Shannon capacity of C5 plus Shannon capacity of this one vertex. This we know, it's square root of 5. And this is 1. And then we observe that we cannot write this in the form a to the power 1 over n for any integers a and n. Yes?
Shannon capacity is always algebraic though, right? It's always an algebraic number. Is it always an algebraic integer?
I don't know. That's true.
Okay.
Do you know this? No, I'm not sure. Right. All right, good.
It's algebraic in every example I've seen.
Is that because it comes from lowest theta number?
Well, the theta function should be algebraic, right?
Right.
But doesn't mean Shannon capacity is.
Right.
How many graphs do we know Shannon capacity?
Right,
Apart
yeah,
from
exactly.
C5 and some trivial.
Yeah.
Okay, so let me finish by saying something about the abstract theorem. So we've focused on these examples of matrices and tensors and graphs. There is an overarching theory. Abstract objects. So what we need to start with is something called a commutative semi-ring. S. So this could, for example, be, so graphs and tensors and matrices are examples of this. So what do we need? We have a set, we have some operation, some addition defined on it, some multiplication. We have an additive unit and a multiplicative unit. Okay. These have to interact nicely. That's what semi-ring means. So it's like a ring, but there's no additive inverse. Okay, so there are no inverses. We can use this element 1. We can add it to itself, and that gives us a notion of natural numbers inside S. So I can think of the natural numbers being inside S by saying that I can add these ones in my semi-ring, n of them, and call this n for any natural number. Yeah, so for graphs, this was this. So for graphs, the 1 corresponded to k1, just one vertex. And for matrices, it corresponds to just a 1 by 1 by 1, a 1 by 1 matrix with a 1 in it.
So what if S is finite?
Sorry. Yeah, we will roll this out later.
Okay, so character.
Yeah.
K1, well, I guess it's the same, but the point is K2 will have no element.
Yeah, so 2 will be K2 bar. Yeah. Yeah, maybe it's natural to put a bar.
So you don't want like 0 to be not just the sum of a bunch of ones, but the sum of anything non-trivial, right? You should somehow think of everything in this semi-ring as non-negative. Like you don't want some graphs that just add up to 0 or
Yeah.
something like that.
I agree. Yes.
Okay.
Yeah. This will follow from the following thing. So we have a semi-ring. There's a notion of natural numbers. And we have this pre-order that I keep talking about, this relation on these elements. And this relation, so we have a relation. And it needs to satisfy certain properties for this theory to work out. So let me call this a Strassen pre-order. On S. So it's a pre-order, meaning it's a relation that's reflexive and transitive. And moreover, it satisfies the following 3 properties. The first is that for any 2 natural numbers, if n is smaller than m as natural numbers, we want this to be true if and only if n is smaller than m in S. Right, so there's the natural ordering of natural numbers, and then we have our pre-order, and these should correspond nicely. That's 1. 2 is, if I take any 3 elements.
N includes 0, right? N includes 0.
Yeah.
Okay.
Yeah.
You're from Euro, so.
Yeah, if we take any 3 elements in the semi-ring, A, B, C, then if A is smaller than B, then I want A plus C to be smaller than B plus C, and A times C to be smaller than B times C. So the pre-order has to respect these operations, the plus and the times. So these are kind of natural, these properties. The third one is some kind of boundedness condition, sometimes called Archimedean property. And it goes as follows. It says that if A and B are any elements, and B is non-zero, then there must be a natural number R such that A is smaller than R times B. So this is saying 2 things. It's saying that any element cannot become too big, because it can always, so in the sense that it can always be upper bounded. Think of B as 1. We can always upper bound A by some natural number. So think of tensors. Every tensor has a finite rank. That's like the analogous statement. Or every matrix has a finite rank. But also elements cannot become too small. So if I take A to be the number 1 and B some arbitrary element, I can always multiply B with some integer to make it bigger than 1. So there are no infinitesimal elements. Those are kind of the two things it says. Okay, so that's the pre-order. Yes?
You don't have to assume that everything non-zero though is at least 1 though, or even that everything non-zero is at least 0. But that will be true in our graph example, but this is not true. We don't have to assume either of these things, right? Like that would, that would make 3 unnecessary, for instance.
That everything is at least 1.
Yeah, everything non-zero is at least 1. But
Yeah, I'm not assuming it. Right. Yeah, it's not needed.
But we don't need it, okay.
Right.
All right.
Okay, so let's make this definition. So now I can define the asymptotic spectrum in this abstract setting as the set of all monotone semi-ring homomorphisms. From S to the reals. That's the same as these 4 properties that I was mentioning all the time. And then, as before, we can define a notion of a rank of an element as a minimization and a notion of the subrank of an element as a maximization. And we can define these asymptotic versions. And under some mild conditions that you do need to check, but they're not very complicated, you will get this duality theorem. So you would get that if you take the maximum over all phi in X, then we get the asymptotic rank. And if you take the minimum, then we get the asymptotic subrank. All right. Okay, good. I think that's it for today.